Today, I'll be talking about ethyl ester production and energy analyses of the transesterification of waste coconut oil using a natural heterogeneous catalyst. This work was done by PHAEDRA JAGGERNAUTH, EJAE John, and PURAN BRIDGEMOHAN of the University of Trinidad and Tobago in the West Indies. So, to put this work in context, let's talk about fuels for transportation. As of 2017, the US used gasoline, distillates, jet fuel, biofuels, and natural gas for transportation. This trend was seen most places as well. However, in the future, we expect this to change quite a bit. We expect this to be a mixture of electric, methanol, and/or ethanol, fuel cells, CNG, LPG, and biodiesel. These technologies, however, can come at a premium price, one that cannot be met by developing countries without significant financial assistance. As developing countries, we have to ask ourselves, what are the most appropriate technologies? A liquid fuel that can easily supplement and later substitute petroleum infrastructure seems most likely in the short term. One such fuel is biodiesel. Biodiesel can be defined as monoalkyl esters, which are derived from oils and fats. It is considered a diesel equivalent. Typically, biodiesel is produced via transesterification. This is a well-known reaction where the alcohol, oil, and either an acid or base catalyst is used to produce our biodiesel and glycerol as the byproduct. However, the conditions for this are not always the greatest. Typically, transesterification reactions are not very sustainable, and this is due to their inputs. Specifically, the oil that we use is typically refined, and this can be quite expensive. The alcohol that is conventionally used is methanol, which is derived from fossil fuels. And often a homogeneous catalyst, such as potassium hydroxide or sodium hydroxide, is used. These catalysts can damage equipment and generate caustic water, and their production can be energy intensive. Furthermore, by using a homogeneous catalyst, we also now have to deal with that in separation, which we know can be expensive and energy intensive. So, what have researchers done to improve this? Well, researchers have tried to replace the traditional inputs with sustainable inputs, and in this work we did the same. Specifically, we replaced refined oils with waste coconut oil. We replaced fossil fuel-derived methanol with biomass-derived ethanol. We replaced the caustic homogeneous catalyst with our benign heterogeneous catalyst. So, waste coconut oil is high in free fatty acids. Specifically, this one has 4.59% free fatty acids. This can cause foaming and low yields if you just do base catalyzed transesterification. So we opted to do a two-step process where we have acid esterification and then base transesterification. The acid esterification was achieved by using a 4:1 ethanol to oil molar ratio for 1 hour at 55 degrees Celsius in the presence of 0.5% sulfuric acid. This lowered the free fatty acid content to 0.79%. Now we're ready for our benign catalyst. The catalyst that we used was a locally sourced red marlstone. These red marlstones were collected, washed, dried, ground, and sieved. Then we calcined them at 1,000 degrees Celsius for 2.5 hours. This calcination process converted the calcium carbonate in the red marlstones to calcium oxide. And calcium oxide is known to be a catalyst for transesterification. After production, we characterize the catalysts. First, we looked at the surface morphology. If we look at the uncalcined red marlstones, we can observe flat, irregular planes and smooth surfaces. However, after calcination, pits and crevices which are associated with CO2 expulsion are observed. We also see increases in our porosity, which means that we would have additional absorption sites for the reaction to occur. We also did energy dispersive X-ray analysis. This allowed us to quantify calcium oxide and CO2 content. As expected, our CO2 content decreased and our calcium oxide content increased. We also looked at the basicity of our catalyst using Hammett indicators. As noted, uncalcined red marlstones have a basicity between 6.8 and 7.2. However, after calcination, the basicity becomes between 10.1 to 15. This is comparable to calcium oxide. So, having characterized the catalyst, now we try to use it in our ethanolysis. The conditions that we used for the ethanolysis were 55 degrees Celsius. We tested 2 reaction times, 1 hour and 1.5 hours, 3 ethanol to oil molar ratios, 3:1, 4:1, and 5:1, and all of these use 15 weight% of our catalyst. Here are our results. As you can see, our yields range from around 30% to 63%. This was pretty good because when you compare using methanolysis with sodium hydroxide, typically you would achieve an 80% methyl ester yield, but you would require a 6:1 ratio at 60 degrees Celsius for 2 hours. If we look at ethanolysis that other researchers have done, while using potassium hydroxide was able to achieve a 74% yield, a 12:1 molar ratio was required. So all of these different results required more energy inputs or more resource inputs than our optimal results. At 63% using a 5:1 ratio for 1 hour. And we tried to keep these at the minimum because we were interested in the energy metrics. The energy metrics that we looked at were the net energy ratio, which is just the ratio between the energy outputs and the energy inputs, the net energy balance, which is the difference between the energy outputs and the energy inputs. These are metrics of efficiency. We also looked at the net renewable energy value, which is the difference between the energy output of the biodiesel and the energy input of the fossil fuel, and the fossil energy ratio, which is the ratio between the energy output of renewable fuel versus the energy output of fossil fuels. So NREV and FER allow us to examine the fossil fuel inputs into the process. Here are our results. We see that we had an NER value of 0.39. This indicates that our net energy ratio is, that our process is 39% efficient. Our net energy balance was negative 120.66. A positive value is required for a process to be sustainable. So our NER and NEB indicate that our process does need to be optimized. However, if we look at our net renewable energy value and our fossil energy ratio, these are positive. So they indicate that the energy generated by the renewable energy product was more than the fossil fuel input into the process. We can also compare this to other work. If we look at the NER of conventional diesel, it is 0.19. Ours is nearly double at 0.39. However, microalgae-based biodiesel has an NER of 0.39, and waste cooking oil-based biodiesel has a reported NER of 1.49. So while we do have some increase in efficiency, some optimization is still required. However, our calcium milestone catalyst did produce encouraging yields at low molar ratios and reaction times. So, this is promising. Furthermore, even though we use less fossil fuel, we know that we need to increase our efficiency. But we do believe that in the long term, our calcium milestone catalyst is a potential sustainable replacement for sodium hydroxide. Thank you for listening. If you have any questions or would like to contact us, please feel free to email us at the address below.